Thanks, Casey. I'll just say at the start, it's been a real privilege to work with Casey and Baptiste and Hattie, and of course the city over these years. And I'm the better scientist for it. So thanks everyone for the opportunity. It's good to see some familiar faces, and if I haven't met you before, virtual hello through Zoom. And I do want to acknowledge that I'm zooming into you today from the traditional, ancestral, and unceded territories of the Coast Salish, Tsleil-Waututh, Squamish, and Musqueam nations, where I live and have deep respect for their traditional relationships with the land and water, and hope to learn from that in environments just like we're in today, where we're trying to figure out water supply for the city out into the foreseeable future. I'm going to share my screen. Let's see here. Okay, so I think what the end result here is going to be that we will learn that the climates that Casey has just shown you and that the city is actively using, that and all of you are considering, are quite plausible given some trends that we're seeing in locally measured climate data. And then we're going to relate that to some climate expectations and give you all real, I hope, a sense of confidence in the information that you're using to make your deliberations about future projects to support local water supply. And importantly, in-stream flow for salmon, coho, and steelhead. Just to remind all of you, and if some of you aren't familiar, all of the results that you're seeing that Casey showed you, those all account for a new set of agreements that the city has entered in with the agencies to better support in-stream habitat for coho and steelhead in your local streams. And you all should be quite proud of what you've accomplished there. So the overview of my talk, there's just two parts. First, I'm going to walk you through some updated historical climate and hydro data. Some of you have seen some of this information before. I haven't talked with you for about 3 or 4 years, so I have updated that information. In the meantime, I've added some new data to the information I've shown previously, and I think it's a pretty clear story is starting to unfold here. And then I'm going to relate that to some expectations around climate change from the work that are coming out of the group that Casey just mentioned earlier with this climate whiplash work. And then with that context, we'll take a look at a couple climate realizations specifically so that you can see how, for example, annual hydrologic conditions that, say, measured at big trees compare to what we're seeing over the past roughly 85 years. So with the historical climate and hydro data, first we'll look at some air temperature trends, and then we will look at some precipitation trends and related hydrologic trends. And then we're going to link that with some emerging climate and hydrologic conditions with expected climate change conditions in the region. So just really quick, why are we looking back when we're trying to look forward and plan? And the basic takeaway here is that it's quite instructive to understand that we're already seeing climate change in the Santa Cruz region. That this is not something that we should read about in the newspaper and think about climate change in the future. It's actually happening right now. That's my takeaway. The data that I'm going to show you come from two different sources. They're here. One is the NOAA Historical Climatology website, and the second is a weather station that's been in operation up at the De La Viega disc golf course. I periodically give the database to Heidi and Rosemary, so if anyone on the Water Commission would like to get their hands on the data, you're more than welcome to do that. We are going to be looking at normalized annual data. So in the sense of air temperature, all I'm doing when I show you the plots in the next couple of screens is, for example, I've taken an annual air temperature value, maybe the average value, and I've divided it by the long-term annual average value. And so in that context, values that are greater than 1 are hotter than the long-term average, and values that are less than 1 are cooler than the long-term average. So we'll start with normalized annual average minimum air temperature. And I'm showing you data starting roughly in 1893 all the way through present. I've updated it just a few days ago out through 2022. So this is the minimum temperature recorded each month, then I average it over the year. And so, the takeaway here is that there's a fairly strong upward trend over time. And roughly beginning in the late 1970s, we have approximately 42 out of 45 years where the values are greater than the long-term annual average. And so that means that we are consistently seeing warmer minimum air temperatures compared to the long-term average. If we fit some smoothing trends to those, so one would be a 2-year moving average in orange, blue is a 5-year moving average, and black is a 10-year moving average. So we're just fitting moving averages to this annual trend. Basically what we're looking for is consistency in interpretation. And sure enough, since the late 1970s, all of the averages are warmer than the long-term average. So minimum air temperatures are getting warmer, upwards of roughly 7 to 8% consistently. We can now look at the same type of information, but now for the annual average air temperature. So we're just averaging the average air temperatures. The upward trend isn't as strong. It's a little more damped compared to the minimum. But if we look at this period since the late 1970s forward, we do see a majority of the data in the annual time step is warmer than the long-term average. So it has a similar response as the minimum does. That makes sense, right? Because these temperatures are being measured at the same location. However, when we look at the maximum, then we start to see a bit of a different story. So now this is the annual average maximum air temperature, and we can see this is fluctuating around the long-term average condition. But when we get into this last 45 years, roughly, we see trends that differ from the minimum and the average temperatures, where we have a strong cooling period, roughly through 2010. Now it's starting to recover, and we're seeing some warmer temperatures. In the De La Viega record, in fact, we see a temperature in September that is the warmest that has ever been recorded at the De La Viega station. So maybe that's a anticipation of things to come in the future. We'll see. We'll keep updating this, but the more recent maximum air temperatures are indeed warmer than average, but the trend is not as strong compared to the minimum and the average conditions. Now, what I want to do is focus in on this latter period, roughly from 1990 forward, because this is the record of the De La Viega station. In De La Viega, we have other information that we can get our hands on, not just air temperature. So I wanted to see if we can see some other indications through different types of data at the station that may give us a hint about what's going on in the local climate. So this is a plot of the monthly average minimum relative humidity. So it starts in October 90, and then these are all monthly values in gray. And I fit a 1-year moving average to those monthly values, and it goes out until just September 2022. What we can see is a downward trend in the minimum relative humidity since roughly 1995. If you fit a linear trend from the beginning of the data series to the end, you still have a downward trend. So in general, things are getting drier. And if we look at the annual minimum values, so annual minimums over this roughly, 32-year period, we again see a downward trend. So things getting drier in both cases. Now I've taken these red dots, which is just the annual minimum relative humidity, and I've just queried when do they occur in the water year. And the water year, again, the calendar for the water year goes from October 1st to September 30th. And when we look at that information, we see a majority of those minimums occur in the late fall. October, November, December. We see a pretty decent contribution from April and also from September. So this, what we're seeing with the minimum relative humidities, things are getting drier, but that dryness is essentially extending the dry season. It's at the beginning of the water year and also at the end of the water year or the beginning of the next water year. Then we can also look at the monthly average solar radiation, which is measured just 1.5 meters off the ground. So it's essentially a plate that is tilted, and it's pointing at the sun essentially, and it measures the radiance, the irradiance, I'm sorry. And what we see over time from 1990 through this past month is an increasing trend through this 32-year period in the monthly average solar radiation. Perhaps this is picking up some indication of variability in the coastal marine layer. I'm not sure, but the combination of the increasing solar radiation with the decreasing minimum relative humidity, that makes sense together, and they both point to warmer conditions and drier conditions. And when we look at the distribution of those humidities, we see that essentially what's happening is the dry season is getting extended. So the takeaway from the temperature information from De La Viega, things are warmer. Annual average and annual average minimum air temperature show a clear increase in trend over the past 45 years, with the strongest increase for the minimum. And in fact, over that 45-year period, on the majority of the years are warmer than the long-term average. And then drier and a longer dry season. So coupled with increasing air temperature trends, the climate data also indicate that the relative humidity has a decreasing trend over the last roughly 30 years. And this is a fairly strong trend for the annual minimums. And the annual minimum relative humidity occurs a majority of the time in April and September through December, so extending the dry season itself. And then the solar radiation is increasing over this time. Okay, so we'll move on now. I can pause here maybe for questions.
All right, let me turn to the commission. I don't see any hands up right now.
Great.
Thank you for checking.
Sure. Now we will turn to precipitation data. And again, we're going to look at normalized precipitation data. So we've taken, for example, an annual total precipitation value, and we're just dividing it by the long-term annual average. So in this case, values greater than 1 mean it's wetter than average. Values less than 1 mean it's drier than average. So here's a plot that it's a little longer. The data series is a little longer than the air temperatures. It extends back to roughly 1877, the fall of 1877. These are the annual total precipitation values from 1877 through the end of the current water year 2022. We can see quite a bit of variability. And I want to just draw your attention to a couple things on this top plot. And it's the dry periods that we're all familiar with. So here's the late 80s to early 90s dry period. And then here, of course, is the 76, 77 dry period. This is the more recent dry period that you all have experienced. And one of the things that's going to pop out in the next few slides is that the dry period you've just gone through over the last roughly 10 years is substantial, and it's the driest in the record that we have. It also has a fair amount of variability in it relative to prior dry spells. And we think this, as Casey mentioned earlier, this idea of whiplash, and I have a result that will bring this to life, is an indication that climate change is here. So again, we can fit these moving averages to the data just to look for trends over different periods. And really the main thing that jumps out to me when I look at this is that's sort of the 5 and 10 year period. And even the 2-year period, we see this declining trend in annual precipitation roughly since about 2000, perhaps since the late 90s when we had that very wet spell, those great ski seasons in 1998 and 99. And clearly this more recent dry period is the driest on record. So now let's take a look at the distribution of precipitation within some examples of dry periods. So we're going to focus on these 3 areas denoted by these black dashed regions. So early on in the record, roughly from the 1917s through the end of the 20s, and then through the 77, 76, 77 dry period, and then for the more recent dry period. And so all I've done here is I've picked 1 year out of each, and I'm just plotting the annual distributions of monthly rainfall. So here's water year 1924, and we see that we have rainfall in 7 months out of that water year, even though it was a quite a dry year. This is 1924 right here. Water year 1977, which, and as part of my work with the city has always been 76, 77 has always been something of a benchmark that we've compared things against. And we had rain in that particular year in what is that? That's 9 or 8 out of the 12 months. And now we look at water year 2014, which was really a completely different condition relative to these two prior examples. If we ignore these very small values, we had rain in 4 months out of the year. And one of the months was at the end of the water year. So for that water year, the period that really matters for water supply and in-stream flows for Coho and Steelhead, we had rainfall essentially in 3 months out of the year. So a fairly big departure from what we've seen in prior droughts. This is another indication of the trends we expect with climate change. We're getting precipitation in fewer months out of the year, right? Rainfall is more concentrated. This goes along with the humidity and the solar radiance results, which indicate perhaps that the dry season is getting longer and drier. Okay, now so we're going to look at both precipitation and air temperature data in a slightly different manner. We're just going to plot it in this quadrant plot here. I'm showing you just a conceptual illustration of that. So when we look at plots over the next couple slides, everything will be within this context. So when you look at the data, anything in the lower left quadrant is dry and cool relative to a historical average over this time period. And the lower right, it's wet and cool. In the upper left, it's dry and warm. And the upper right, it's wet and warm. These would be where we would expect, climate change conditions to manifest in the future. Anything that plots right in the middle is just consistent with the long-term averages for precip and air temperature. So I'm just moving some things around here. All right. So here is a plot of data since 1964. So we're looking at 64 through 2022. One of the things you'll notice immediately is a majority of the data points lie above the 1 line on air temperature. So we're warmer than the long-term average. And it's roughly an equal distribution in terms of the precipitation relative to the mean, drier and wetter. But I've colorized the more recent time period from 2013 through 2022 because here is where we start to really see some of the indications that we have been told to expect with a future climate change condition. So the cooler colors start in 2013 and they get increasingly warm in hue as we get closer to the more recent period. Okay, so this idea of whiplash, we see it in the data itself. And if we look carefully at the precipitation trend time series, we would have noticed it as well. But here we start in 2016. 2016 was somewhat of an average year. And then we go into 2017, which we know was quite wet. And in 2018, we bump backwards substantially. And we have a very, very dry year relative to the prior year. So this is a fairly big swing in precipitation. However, all consistently generally warmer than the long-term average. Another thing we see is that 4 out of the last, what is this? That's 9 years are the driest on record. And then when we expand that to 4, 5, 6, 7, 8 out of the last 9 or 10 years are dry, or you could even say 9 out of 10 are dry relative to the long-term average. So this more recent period has the driest years that we've experienced in the Santa Cruz region. and on majority are dry relative to the long-term average. That just provides a little more context about that time period. Now we can look at the same data just slightly differently. So on the x-axis, we're plotting total annual rainfall, and on the y-axis is the time. So we start down here at 1877, we go through 2022, and then we have colorized the data relative to the number of months with more than 1 inch of rainfall. So that the dot color tells you how many months rainfall was received in that water year. And one of the things I want you to notice is that up until about 1930, most of the time, or all of the times, the water years had 4 or more months out of the year where we had rainfall, right? And then we hit the late 1930s or mid 1930s, and we see the first occurrence where we have a water year with 3 months with more than 1 inch rainfall. We go quite a bit of period of time until roughly 1959, and then we hit 3 again. Quite a bit of period of time until I think it's 1989. We have 3 months, and then we enter this more recent period, and things start to really change. The big change is that now we have water years where we're receiving more than 1 inch of rainfall in only 2 months out of the year, and now that's coupled with water years around it where we're getting 3 months out of the water year of rainfall. And of course, we still have some variability. This is, in fact, 2017 out here. So not only was the more recent period drier in terms of total precipitation, it was drier in terms of the number of months in which you received rainfall. These are all things that we have been told we should expect in a climate change future. So i.e., climate change is happening. We can also take a look at flows at big trees. So this is the total annual flow at big trees for the period 1937 through 2022 on the water year calendar. You've all seen many plots like this. I've just updated it through 2022. So the warm colors go from critically dry, and then green is average, and then the darkest blue is very wet. And I'm just calling out a couple different points on the plot. One is here's the late 80s, early 90s drought, and you can see that it was severe in the Santa Cruz region, largely because of its duration. It's 1, 2, 3, 4, 5, 6, 8. 6 out of 8 years were critically dry. A 7th was dry, and then we had a wet year intermixed in there. We fast forward up to the more recent 10-year period. We see a similar run of climate where we have 1, 2, 3, 4, 5, 6, 7, 8 out of 10 years or 11 years that are critically dry or dry. We have this whopper of 2017, which is the largest flow in terms of total flow on record, and then a wet and an average condition. So Casey was talking about the coefficient of variation earlier in terms of precipitation. We can see quite a bit more variability in the more recent record of big trees, and that's just a reflection of the variability that we're seeing in precipitation. So summary of the precipitation and hydro trends. Dries are getting drier and consistently warmer. The 4 driest years on record have occurred in the past 9 years, and these were all warm relative to the historical average. We have a drier and longer dry season itself. Dry years are increasingly receiving rainfall in fewer months of the water year, leading to a longer seasonal dry season. We're starting to see this wet to dry whiplash, or the reverse, dry to wet whiplash. In the past 6 years, the region has experienced a whiplash effect going from the very wet 2017 to the dry 2018. It's the largest precipitation swing since 1900. And then the dry periods are getting longer. Precipitation patterns over roughly the last 35 years have resulted in 5 to 8 year periods with the majority dry to critically dry water year flow types for big trees. And that did not occur prior to that time period on record, the records we have anyways. Okay, so you all have seen this figure before, but I think it's useful to revisit. it in the context of this updated climate and hydrologic information. So this is a diagram that was produced by Daniel Swain's group out of UCLA. And it's an indication of some expectations that we should have for future changed climates in the state of California. So it's roughly divided between northern and southern California. And it looks at extreme dry years, extreme wet years, dry to wet whiplash, and severe storm sequence. So in the extreme dry years, like water year 2014 and 2021, they expect, a near 2-time more frequent occurrence of these. It's hard to say if we're seeing that in the more recent climate, but we are certainly seeing more extended dry periods relative to the prior 60 to 80 years. Extreme wet years, like water year 1998 and 2017, there's an expectation of a roughly 2.5-time increase in the future changed climate condition. Dry to wet whiplash, like the 2017 to 2018 sequence, it's a little more than a 1.25 times more frequent in the future. And then this idea of a severe storm sequence, 1998 and 2017 are good examples. 2017 is a really good example. We had the reasonably large rains in January, and then substantial rains in February on top of saturated conditions. That would qualify as a severe storm sequence in their parlance. And they're saying that we should expect a 5-time as frequent occurrence of those relative to the historical. So the point really with reviewing this is that we're starting to see each of these categories manifest in the local climate and hydrologic records. And so this supports this notion that climate change is not a future thing, it's here. You all are experiencing it already. Okay, so just a few more slides here. Now we're going to try to relate some of the ideas or the findings, I should say, that we just reviewed and take a look at a few climate realizations that were developed by Casey, Baptiste, and Hattie that have been used for a lot of the work that you all are considering and thinking about. And in particular, we're going to look at 2 climate realizations that come out of this realization 2770 and this realization 1270. And this is a plot that was put together by Casey, Baptiste, and Hattie. It's just to give you an idea of on the next 2 screens where these 2 realizations sit relative to the other realizations that perhaps you heard about, and relative to the great number of realizations that they've developed, right? They've developed over 8,000 different future climates. Okay, so here's climate realization 1270. And in this case, we're looking at the climate condition where there is no change in temperature, there is no change in precipitation, there's only a change in the coefficient of variation. And it's just like the big trees hydrologic condition flow plot we just looked at for the historical period of record, 1937 through 2022, in its construction. So the colors are all consistent. So critically dry would be the darkest red, out through very wet would be the warmest blue. And I've calculated these hydrologic conditions based on the categories that you calculate with the historical data. So we're comparing apples and apples here. And a couple of things to note in this realization. One is we see a whiplash event clearly in this realization. It comes in at 2048, where we have 3 years in a row. 2046 and 47 are critically dry. 2048 is a dry year, and that's subsequent to a very wet year in 2049. So the point is here that is some of the information you're considering has these sort of climate effects embedded in them that we are told we should expect in a future climate change, future change climate condition. And then later in the record, we have a fairly extended dry period. It starts in 2086, it extends through 2097, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 12 years are critically dry or dry. So that's a little extended compared to the records we have for the historical period, where we're looking at 8 or 9 years, where we have the majority of dry or critically dry years. But it's this, similar concept. Extended dry periods, more intense dry, and consistent with what we're seeing in the more recent climate. Here's a different case, this climate realization 2770. Again, no change in air temperature, no change in precipitation. Again, a coefficient of variation increase of 20%. A couple of things about this time series. You see this 4 very wet years stacked up against each other. Of course, we can't predict what any individual storm in those years will be like, but the idea that we have 4 in a row and 2 very wet years that are quite wet, it's not a big leap to imagine that there will likely be some severe storm sequences within those, and linking up with the UCLA research. And then if we look later in the time series, again, we see another climate whiplash effect, where we at 2095, we go from critically dry, and 2096, we go to very wet. And then just that follows on the heels, or this comes right after another extended dry period. It's roughly 11 years in length, and 1, 2, 3, 4, 5, 6, 8 out of the 11 or 12 years, I guess 9 are dry or critically dry. So the realizations we're using, that you all are considering in your deliberations, include the trends and the characteristics we're seeing emerge in the local climate records. They're consistent with what we're told to expect for the future changed climate conditions. And so they're plausible. They provide us with a good basis for trying to think about and understand how different versions of the water supply system, which account for in-stream flows, will serve the city and its residents under these various conditions. And I should say we also see, similar characteristics and trends in all the other realizations. It's just would be a different sequence, maybe a little more magnified or less magnified, but they're all within these other sequences as well. So I've just pulled 2 examples out just to show you. And that's it for my update to you all.
All right. Thank you, Shawn.